Uh, Hello guys, welcome to another video. In this video, we'll be predicting median house pricing using XGBoost, that is extreme gradient boosting. XGBoost is an important machine learning model that builds on top of boosting models, and we'll talk about it. We'll use Python for it, and in the end, we'll divide our code into different parts and make different blocks or like going towards the leaf node. So let's start with the concept first. So XGBoost is extreme gradient boosting. It is a powerful machine learning tech model and algorithm which is used as an implementation of gradient boosted algorithms, decision trees basically, for speed and performance. So what are decision trees? Each decision tree has a output either yes or no, and it splits the data by going from the root node to the leaf node to reach its final value. uh, why do we split nodes? Because the decision from a single root node is not that efficient, and by the time we run a depth first search or a breadth first search and arrive at the final node, we'll get a much better output. So, what's the strategy here? Here we use a concept called boosting. Boosting is basically an ensemble technique where multiple models and outputs from multiple parts are trained sequentially. Instead of training the trees or nodes independently, we train them sequentially one by one, as each new tree focuses on errors and reducing the errors made by the previous ones. So, first tree 1 will be trained, then tree 2 will be trained. Tree 1 will iterate and provide some error, but tree 2 would try to prevent those errors already made by tree 1 and try to predict the output that is much more closer to the final target value. So XGBoost consists of extreme part to it instead of simple gradient boosting, and this is how it handles optimizations and regularization. So in it we have inbuilt L1 and L2 regularization. L1 is lasso regularization, L2 is ridge regularization. Both of these are used to prevent overfitting, and it is the distance and the square of the distance from the final target value from the input value. So, XGBoost automatically learns the best features from the right and left branch based on its previous training on previous trees, and there is also parallel processing going on. So, there is a lot more parallelization. We also like talk about pruning and tree pruning because depth first approach is really optimal at finding optimal splits, and whenever like we encounter a negative loss, that's when it stops performing. So why should you use XGBoost? Because it is great at its performance and produces highly accurate machine learning models. It is really efficient, utilizes hardware resources like CPU and GPU, and also performs parallel processing. It is also flexible, can be used for regression, classification, and ranking models when you want to predict numbers or predict different categories. So let's get started with the workflow of code. And this is like referenced from the hands-on machine learning book with scikit-learn, keras, and tensorflow, and it's from chapter 2 of end-to-end machine learning project. And let's get started with the code. I'll share my screen. So let's start with the setup first. um, First I'll import the Python. So I'm gonna import sys sort sys. We'll import scikit-learn and version 20. Let's do imports.
It's 6 o'clock.
Import numpy as np. Import pandas as pd. Import os. If we wanna plot figures, we're gonna do matplotlib inline xtick, ytick, and axes. So we'll first get the data from the internet, and so let's get the let's import a zip file, import tar file. We'll import url request. Let's make download underscore url equal to. We'll use hands-on ML. Géron housing. So this is the link. Datasets housing, and this one is the one which we want to import. So we'll get the link from here. Go back to our notebook. Yeah. Now let's do data underscore path to os.path.join. We'll join it with the data root. Gonna do dataset housing. Yeah. Next, if not os.path.is directory, if it's not in the directory, then we'll make a directory. os.make dash directory path, and then this is the path of the zip file, and we will retrieve it, zip it. Also, let's make housing. We'll open it and extract all, and then we'll close. Let's see. Let's connect to 800 GPU to run this first. I'm sorry, should be data path. Okay. Dataset housing, if not data path, make data path. XGBoost housing, URL lib request, URL retrieve. Why is okay? Let me check this error once. Oh, I used a wrong version. copy raw GitHub user content. Okay. Okay. Download files extracted to dataset housing. So here we have the file. We have its CSV and TGZ. Now let's print and visualize the output. So we're gonna do CSV underscore path equal to join it, and then we'll print housing dot head. So we have different parameters like longitude, latitude, median age, total rooms, total bedrooms, population, housing, median income, median house, ocean proximity. So whenever we want to predict a house, these factors are the most important, but we want to chalk down the factors that look unimportant and also get the baseline of it. So in my opinion, bedrooms, rooms, medium income, house value are important. I don't know if latitude and longitude would be that important. So okay, let's start. Data frame functions. So head is used to return the 5 rows. Info is used to get quick description of data. Value underscore counts. Find out what categories exist and how many districts belong to each category. Describe is used for summary of numerical attributes. List is used for histogram, showing number of instances that have a given value range. So these are like some functions that are for visualization and should be used before like proceeding ahead with your model, because it's important that you get an idea of your features and most important features. So let's do housing.info first. See what we get. We have longitude, latitude, median age, and you can see there are some missing points here. Rest all data is balanced, everything is float 64. Ocean proximity is an object. Do we need this? That's another question. So total bedrooms. So now let's see housing proximity. It's a object value. It's a numerical. So we'll see what count we have. See, it has classes island, nearby ocean, inland, and less than 1 hour ocean. So this is the count. What's the maximum here? This one is maximum. This is the minimum. Now let's do housing dot describe. So we are seeing the mean standard deviation for each. This is the median income household. And see 499 household population is 1455. And this is the median house price. Okay. Now let's plot a histogram. Housing dot hist is equal to 50 figure size this plt dot show. For each variable we can see this looks like some look like normal distribution, some are uneven. Longitude, latitude, median age, this is like maximum. I think some values were cropped after this is why it's showing the maximum value. We have total rooms, total bedrooms, population, households, median income, and median house value. Okay, now let's create a test set. So we will pick some instances randomly, 20% of the data set, set them aside. Okay. So np.random.seed to 42. 42 is the answer to ultimate question of life, universe, and everything. That is the significance of number 32. My professor told me that. Okay, so we set the seed. Now we're gonna do from sklearn.model underscore selection import train test split. We're gonna do train underscore set test score set equal to train test split housing test size, and then we're gonna visualize a test set. Okay, now we'll visualize the data. So we will look for correlations in the data. Core method computes the standard correlation, also called Pearson's R, between every pair of outputs. So basically, how is your one feature related to the other feature? How close is it? The correlation coefficient measures only linear correlations. It misses out on non-linear relationships. Another way check for correlation is to use pandas scatter matrix function. Which plots every numerical attribute against every other attribute. Okay, so as ocean proximity is an object, we're gonna convert ocean underscore proximity column to a numerical representation. How do we do that? So we're gonna do housing score for correlation equal to pd dot get underscore dummies. We're gonna use this column ocean proximity, and let's do correlation matrix. We'll also do a median house value and sort it using ascending value. Let's print this as well. Print housing for correlation head. So we converted all the like ocean proximity into true and false. Like this is the get dummies function. For ocean, it's like false, false, false. For nearby, it's true. So it divided it into classes. And here, what we did is we made a correlation matrix and sorted it in the form of an ascending order. Let's see what correlation matrix is. Table showing correlation coefficient between multiple variable indicating the strength positive and negative. Okay. Right, so it's something like that. Some are negative as well. So now we'll do from pandas dot plotting import scatter matrix. We will plot median house value, median income, total rooms, and median age. Let's see what we get. So this is like the relationship matrix between variables. Let's do housing dot plot kind. Let's do a scatter plot equal to median underscore income on one, and let's plot it against y, median house and alpha equal to 0.1. Plot dot axis 0 comma 16 comma 0 comma this is the plot. So some can be like tail heavy, some can be head heavy. So we'll now experiment with attribute combinations. Some attributes have a tail heavy distribution. So we transform them. So we're now like prepare the data. Feature engineering. So we're gonna do how we'll drop the unnecessary columns, train, score, set, drop. So from training we'll drop the target score underscore value. We'll do axis equal to 1. This is gonna be our y at our target. Okay. Now missing data. An attribute that has some missing values. We have 4 options basically. So first what we can do is we can get rid of corresponding data samples by using drop NA function. Also get rid of the call attribute column by drop function and set the smallest set some actually not the smallest set, we can set some values to 0 mean median for by using fill NA or applying simple imputer method class from scikit-learn. We can make new columns and getting what will be imputed. So any of these methods we can use basically to treat missing data. Okay, let's go with method 3. Let's try method 3. So what we're gonna do is we're gonna from sklearn.impute import simple imputer, and then we're gonna declare a variable called imputer. We'll use the function simple imputer and pass strategy equal to median to it. Now let's make a variable called housing num, and we will drop our column which is like unnecessary for now. It's an object, so we don't need it. Portion proximity comma access equal to 1. Then we're gonna fit housing num. Okay, so this is our strategy. Now let's do imputer dot statistics. So we can see this is like different values for like our median values for different columns, I think. Yeah, let's do housing median values. It's the same basically, median values. And now we can see we can like transform imputer dot transform. We're gonna then create a data frame consisting of this transformed version. Columns as housing name column, same as the column names, and index would be housing num index. Now let's print this transformed version. Housing underscore. It shouldn't have any missing values, I think. Okay. Now let's work on categorical data. For text or categorical data, here are 3 options. This is option 1, drop categorical columns. Is ordinal encoding. Assign each unique value to a different integer by using scikit-learn's ordinal encoder class. What's the third one? It's called one hot encoding. We create new columns indicating the presence or absence of each possible value in the original data by using one hot encoder class. Let's see the difference between ordinal and one hot encoding. See here. So basically label encoding is categorical 1, 2, 3 for different categories, but here you can see Apple is chosen 1. So here we label it in terms of zeros and ones. Okay. So here we label in terms of 0 and 1s. That's the difference. So now let's see the head. So housing categorical equal to housing ocean proximity. So this is like for near ocean, inland, for 1 hour ocean. And we'll use like one hot encoder. One hot encoder as an example. We'll do from sklearn dot pre-processing import one hot encoder. We'll use this function called fit transform on this housing cat consisting of ocean proximity, and let's see, compressed sparse row matrix of data float 64 with 1652 stored elements and shape. This will display the array housing cat to array. Let's see how it looks. So yes, for each active thing we have like 1 on it, and rest all become 0. Let's observe the categories. Cat encoder dot categories. So we have less than 1 hour ocean, inland, island, near bay, near ocean. Okay, let's perform feature scaling. With few exceptions, ML algorithms don't perform well when input numerical attributes have different scales. Basically, it should have similar scales to measure or compare. So there is a note basically. Should note that scaling the target value is generally not required. There are 2 common ways to get all attributes to have the same scale. First is min-max scaling and another is standardization. Let's talk about both. So first is min-max scaling, also known as normalization, is the simplest. So here values are shifted and rescaled so that they end up in the range from 0 to 1. So we scale everything to get between 0 to 1, and we do this using a transformer function by scikit-learn called min-max scalar. What's the next method? The next method is called standardization, and it subtracts the mean value and then divides it by a standard deviation so that resulting distribution has a variance, unit variance. Standardization is much less affected outliers. We do this by using standard scalar function from scikit-learn. As with all the transformations, it's important to fit the scalars to training data only and not the testing data only to the full data set, including the test set. Only then you can use them to transform the training and test set. Okay, so these are like the basics of feature scaling. Let's see min-max scaling versus standardization. This is the formula: min-max normalization, standard Z score, x by mean, then standard deviation, max mean, max. Okay, this is the difference. Now let's make a transformation pipeline. So we're going to do from scalar.pipeline import pipeline from S pre-processing import standard scalar, and we're going to define a pipeline using the pipeline function. We'll use imputer, simple imputer, and we'll use scalar, standard scalar. We'll fit this and then we'll print it housing tr. So everything has been imputed and median strategy has been used. We also use standard scalar in it. So standard scalar is basically x minus mean upon standard deviation. Okay, now we're going to do column transformation. So we'll do from sklearn compose import column transformer, define underscore attributes equal to list housing numbers, and cat attributes is basically categorical attribute is only one ocean proximity, and our full pipeline consists of column transformer consisting of num pipeline and num attributes and cat variable of were not coder and categorical attributes. So we basically fit it fit transform, everything fit to fit transform, fit and transform into a single convenient call.
So I was like, just going to Memorial Park. Yeah. And down the street.
Okay, let's see. So this is our data. Let's observe its shape. Dot shape. So it has 1615 rows and column, 13 columns. Now we'll select and train an ML model. Let's use three models basically. We'll use linear regression first. We'll use decision trees, then XGBoost. Let's see. So let's go with linear regression. So we're gonna do from sklearn dot model import linear regression, and we'll fit it on housing prepared and housing labels. Let's try a few training instances. We'll do some underscore data equal to housing dot iloc 5, some data prepared, and we're gonna make predictions. We'll also print labels. Yes, some labels. Okay. So our prediction is this. These prices with these labels. So now sklearn.metrics mean square error, we're gonna check and predict how it performs by using mean squared error, housing labels and housing predictions. We're getting a value 68,433. Okay. Let's try mean absolute error as well. So it's giving 49,000 and this is giving 68,000. Model is underfitting. Features do not provide enough data to make good predictions. How to fix underfitting? Select a more powerful model to feed the train algo with better features. Now let's try decision trees regression model from sklearn.tree import decision tree. And then we're gonna pass random state 42 to it. Let's make predictions. Predictions using predict function on prepared, and then we calculate mean squared error. Now let's do cross validation. On sklearn dot model underscore selection import cross val score. We'll create a function def display scores, which takes in the parameter score. I'm gonna print scores, mean, and standard deviation. So create another function called model underscore cross underscore val underscore scores. Cross validation scores. So basically we calculate negative mean square error for 10 samples. Use 10 square root of negative. Then we return model RMSE scores. Just a second. Okay. Turn model RMSE scores. We will use. Okay. Now display underscore score, and we're gonna pass model RMSE score. We're gonna evaluate decision tree and linear regression. We'll basically say print decision tree cross validation model tree reg. And we're also gonna print linear cross validation linear reg. Let's see. It's gonna take some time. Meanwhile, let's do for random forest. Okay. From sklearn random forest regressor. Estimate on this housing labels. Print forest class validation. For SM as well we did. Then we're gonna finally do XGBoost. Let's pass score estimator equal to 100 and n underscore jobs equal to 1. Okay, we have our linear regression results and decision tree result. Let's look for decision tree again. Okay, I'm gonna check this up once. Okay, here decision tree regressor I used. क्या? I'm using classifier only. Should I use regressor? Okay, let's try using regressor. I'm gonna try and check this error. Your code is not technically correct, but error warning sign is a breakdown. Perfect. So I know seeing an RMSE overfitting the data. The decision tree by default will keep growing until every single perfectly categorized. Okay. Max depth and random state 42. Let's try this. divided for decision tree CV. Okay. Now let's run random forest. That's the inference here. What is inference here? So linear regression is overfitting, that is underfitting. Let's read this. Okay. So linear regression is underfitting and overfitting. For random forest. Train model on full training data. Will evaluate on the final test. X underscore test as a drop median host value access 1. Then we'll keep it to the target. We'll transform predictions as final model predict prepared, and we'll compute the mean squared error. Print final RMSE on test set. Did we get an output? It's still running. Let's one by one see how these all models work. Let's go with linear regression first. Housing prices. Linear regression model for housing prices predicts a home dependent variable based on features like square footage, bedrooms. So B0 B1 size plus bedroom. It works by finding best fit line or plane that minimizes production errors. Tricks like RMSE. Choose features and target. Equation. Model learns best beta values from historical data and uses it to predict the prices. RMSE explains the average magnitude of prediction errors. R square explains the variance. Residuals is difference between actual and predicted. Okay. Now the next model. Did we get an output? Okay, we got an output for random forest cross validation. We put this and ask is the inference here. Best model ensemble technique 48,000 more accurate. Reduced variance, slightly overfitting though. Paste this here. Let's run SVM, then XGBoost, then evaluate it as well. Meanwhile, let's go and we know key linear regression gives us the best line of fit. Now let's go to decision tree. Decision tree. A decision model predicts the mean price of a house by recursively partitioning data into smaller, more homogeneous groups based on specific features like location, square footage, and number of bedrooms. The predicted value for any house is average of actual sale price, all training that fall into same group. Building a decision tree involves feature, scale, selection, and splitting. The model starts with entire dataset and evaluates all features to find the single best features and threshold to split the data. And it minimizes the variance. Recursive partitioning. This splitting process is repeated for each new subgroup until a stopping condition is met, such as reaching maximum tree depth. The final unsplit groups are called leaf nodes. For any new unseen house, the model follows the decision rules to a direct specific leaf node. The predicted price is mean price of all houses in that specific node. Average area income 70K, go left. Number of bedrooms is 4, go left, go right. Okay. Grid search visualization. Okay. Root node, child node, branch. This is splitting. Cluster of all samples, sample of parent node, child node. Sort the sample, mean, cost, repeat. Okay, I think this is confusing. Okay, did it happen?
It's 7 o'clock.
extend this model score cross well scores. Okay. Make an inference. Swim is a poor fit. Standard simple. Generalizing well. So this is our inference. Give a summary of everything and result. The performance were evaluated by using RMSE root mean square error. So linear regression, underfitting, decision tree overfitting, SVM poor fit, random for a strong contender, XGBoost is top performer. So this is like minimum lower RMSE is more accurate. Okay. Okay. Paste it here for my reference. And now let's see how SVM works. SVM is a powerful tool for handling complex and nonlinear relationships. Careful parameter called C, which is best fit line. Instead of classification, SVM uses regression to estimate continuous house prices, fitting function to minimize error. Kernel function like RBF or polynomial allow SVM to map into higher dimension and make another plane capturing complex pattern. Feature importance also we can find complex, memory efficient. Okay, is there like any other thing that I'm missing? Let's find the most important features. Forest reg dot fit housing underscore repaired comma housing labels feature underscore importances cat underscore encoder sorted this as well. Let's see its inference as well. Inference here. Let's read this. Wealth, the feature median income is most important variable, 49%. This median income. Economic status indicator, location, land, longitude, latitude, geography. Land is the most important feature. Island and nearby have almost zero importance. Okay, so we basically coded the XGBoost and got the final result of this with a low RMSE square. Lower RMSE means more accurate model. So yeah, this was it. Thank you guys for watching this video. I'll see you in the next video. I am in USA. So yeah. Artificial neural networks. I think I'm gonna cover artificial neural networks and Hugging Face next, and Google Cloud as well. But mostly in the live sessions because I'll be coding. I have an exam coming up on deep learning like in a day or two, so I'm kind of practicing right now. Thank you guys for watching this video. See you again.